check the audio stream. I'm going to go ahead and start early and leave early. Okay, so what I'm going to do, I'm going to make up a problem. Looks like so. So this type of connection is designated that the pipe continues. So I'm going to take a slice here. Call this 1. I'm going to see the area here. Now the numbers may not turn out to look very good, but in the sense that I might get too fast velocities or something. So say I have 2 feet. Oh, okay. I have 2 feet squared. Area 2 is equal to half a foot squared. This area 3 would be 2.2 feet squared. And this area 4 would be 0.3 foot squared. And we're going to say, first thing I'm going to say, let's say the velocity in here is, let's say it's water. Density is 1.94 slugs cubic foot. I don't know, 20 feet per second. So I'm going to figure out the Q of 20, or here, A times V. So we're going to assume all of these are jettisoned fluid out. And then the key is somebody came in here and welded a piece right here to hold this. There's one weld right here and it's bolted, so essentially what you're having to do is you're having to produce put it in a particular direction, and it may end up changing signs, but you're having to hold it with an FX and an FY. So what you have is 20 times 2, or about 40 cubic feet per second. So with the information I've given, I can't figure out the exits velocities unless I have some information here. So what I'm going to do is I'm going to go ahead and make this assumption, because I've got to do this here. I've got to do this to solve the problem. Okay, let's see. Here. 1 and 2. All I'm attempting to do is move it down the page. There we go. And with the escape button. Okay, so I moved the whole problem down the page. So I'm going to say, if we've got 40 QN will be 40, so this one, and this one all have to add up to be 40. So I'm going to say, and this can happen easily. I mean, I could restrict the flow down here and then widen it so that even though this is a particularly larger area than this one or this one, it could have a lower amount of fluid through there. So I'm going to assume that this is 20 CFS. That gives me, and I'm just going to make it 10 CFS out of here, and 10 CFS out of here, cubic feet per second. So that gives me M dot out, 10 and 20 and 10 gives me 40. So I have satisfied that. So now what I need to do, I need to find the velocities. So I'm going to basically slide these over and say this is equal to velocity 2 times 0.5 is the area here, and therefore velocity here would be 20 feet per second. So let's look down here, move it to the side. Let's say 20 is equal to V3 times 0.2, or V3, which would be 20 divided by 0.2, be 10 feet per second. Okay, let's we've got 20 divided by 0.2, 10 divided by 0.1. What am I doing here? Here, let me just. That is not where I want to go. That's not where I want to go. That's where I want to go. But then I want to go back here. So, just making sure. Oh, 100. Sorry. Just make sure this other one is correct. 10 divided by 0.5. 20. Yeah, I got that one. And let's go in here and figure this one out. Okay. So what I have here are V4 is equal to, oops, what's going on here, 33 and a third feet per second. So let me designate or go in and say we've got this one, this one, this one. Here's your area, here's your area, here's your area, here's this one, and here's your area. The key is, what we're going to find is, what is these forces? So, if you look back at the Reynolds transport, it says something like this. Is equal to partial with respect to time of the integral over the whole control volume of a little b, oops, I don't know whether to put the b before or after this, d volume plus an integral that goes around the whole controlled surface of a b, I guess the rho would come first, v dot n and dA. So this is Reynolds transport. Now let's make a little table. B in the equation. So if you put in, okay, now let's review what this means. So this, you have to use your brain and think differently. Think different than what's on the right-hand side. So what you're doing is you're thinking older memories here. And so let me give you an example, and I'll do it with the first one. So here's my first part of this table, and I'm not going to make the table go too far. Maybe I'll just make it go to 2 for sure. I don't even know if I'm going to do the third one right now. M. Now, if someone took a system, like for example what you did in thermo, took a cylinder, and you put a piston in it. Here's your piston, and you put a weight on the top of that. And then what you considered was all the gas that was in here. That was what was determined as the system. So usually it's a fixed mass system. And so what you usually do here, not because of this, but this is a general definition. So this is the general definition of what the little b is. So if you take the big B to be this, this becomes 1, and this becomes a continuity. But let's think about it like this. Let's look at this. What is the change in the mass over T? Your thought process should go to the system, which should be right here. And what is the change of mass in a fixed mass system? It should be 0. And so actually, what I'm going to do here is I'm going to add a portion to this table that's going to be left hand side, or d dt, and what should go here should be 0. So if you look at this equation, that's what you get. So let's experiment here. And what I'm going to do next, I'm going to go ahead and do this one. Now, what we're eventually going to do on this problem is, and I'm going to move all this out of the way in a minute, but what we're going to do on this problem is we're going to go after the forces. So you can't use momentum to go after forces because it's basically conservation of mass. That has nothing to do with forces. But now you look at the left-hand side here, and what I'm going to do is I'm going to write the left-hand side, then I'm going to move it down. So the left-hand side here should be this. Now, there is an equation which is F is equal to ma, but actually that equation is better expressed this way. Oops. And I'm going to tell you why. I'm going to tell you why it's expressed usually this way. Okay, this is actually the momentum equation. This is too, as long as the mass remains fixed. However, it's introduced to the general public this way. You were taught this a long, long time ago. F is equal to ma. But the actual equation is this. Why are you not taught this from day one? Well, because you would have to explain what is that d and what is this dt. What does that mean? So if you go describe that to like an 8th or 9th or 10th grader, they haven't had calculus yet and they're completely lost. However, if you go in and you explain it to a college person who has had calculus, you can describe it this way. At this point, you've had this. So now it turns out that this capital D and this capital D are the same. And you read back through the text as the designation of why they capitalized it there. But this equals to this. And actually, this should be there as well. So suddenly you realize the left-hand side, yes, becomes this. However, on the left-hand side here is actually sum of the forces. And this becomes linear momentum, or conservation of momentum, depending on who you talk to. It could be written both ways. I'm not sure I'm going to fill out the last row yet, but I can save this and fill it out later. So in essence, here's what you're doing, okay? Let me select this table, move it to the right, and fill it in with another portion. So I'm going to move it to the right. And what I'm going to do is do something interesting here. What I'm going to do, I'm going to say equals to, and basically I'm saying dm dt equals to 0. So what I'm going to do here is dmv dt equals to this portion where you went from here to here, or from here to here, had really nothing to do with the Reynolds transport. It was basically the fact that there is another equation somewhere that says, okay, change in mass of a fixed mass system doesn't change. And then it says the change of mv, which, what is that? So there is another equation there. F is equal to dmv dt, and that becomes this. This had nothing to do with Reynolds transport, neither did this, but yet out on the left side popped this term. Okay, so I'm going to say this term appeared in the Reynolds transport. Equation. So this is a bad title to, so this term appeared in the Reynolds transport, this one appeared, then I replaced it. So I used another, some type of other information to replace that term. This term got replaced with that term. So now we see where this is coming from. How do we implement this? Well, now that we kind of know what this is, let's sort of look at, now we're not having to deal with the continuity here because we already dealt with it. So I'm going to look straight at the momentum. And in doing so, I'll just keep it there. Okay. So take this term, put it right here, and write it down, and then take this term, put it in, well, sorry, not that term. Take this term, put it in right here, and right here, and what do we get? We get on the left side, sum of the forces in a vector form is equal to the partial with respect to time integral over the whole control volume of, now what I do, take this V, put it in right here, and I can put the row in front of it or after it, doesn't matter, the volume. So this V and this V are different. One's the volume, one's the velocity, and then integrate over the entire control surface of V left up there by itself times rho V dot N dA. Let's talk about this term. This is a dot product. Therefore, it's a scalar. This is a vector. This is a vector. And this is a vector. How do we break these apart? Well, pretty simple. And I'm going to use the magic that I have here to break them apart. Here's what I'm going to do. Here becomes the magic. In this problem, I'm only looking for X and Y. So I'll do a copy, and I'm going to put one right here. And then I'm going to put one about right here. Okay, so now what I'm going to do is go in with this pen, and I'm going to turn this to the component. I wanted that to be a different color. Yeah, we'll do it that way. Now go in here, taking the component, and suddenly you see you have two equations. Now you would have three but I only have this in 2D. So I'm only going to look at two dimensions, the force in the X and then the force in the Y. So because of that, I'm not doing the others. I'm not doing the Y, I mean the Z. Let's make another assumption. The other assumption is steady state. Steady state will tell you that this and this don't change with respect to time. So guess what happens? I can actually recopy the same junk down and use the magic of the pen. Copy, paste, but now guess what? Those terms are gone because it's steady state. And use the magic of the copy, I can just put them up there. Now what's the next thing? The next assumption. Here's the assumption I'm going to make now. Let's take a particular exit. And let's say you had a profile of a velocity that looked kind of like this. When it went up like this, it went fast and it went slow. But now I'm going to make the assumption of the average, in which I basically take the average velocity being constant across the whole exit. So then I'm going to put that in here. So if I'm integrating and dealing with averages, then I can just do a summation. Here's what I mean. Next, copy, drop it about right there. This time I am averaging it. Okay, take the D. Now I'm averaging over the whole control surface. So this turns into a summation over the entire control surface and a summation over the entire control surface. So now I'm sitting here and I've reduced it down to the point where I can actually use this set of equations to solve my problem. Now, often this is where you'll start, but I wanted to go through that process that we had there to take us through. Now, what I'm going to do is copy my problem, get all the way down to the bottom, put the problem here next to what I've got. Now, I'm going to also do something interesting here. Do a copy, I'm going to do a paste. But I'm going to slide it over to about right here. And then I'm going to put it kind of this equal sign here. So what I'm going to do with this right, now what you've got, look at the equation. On the left, I've got forces. On the right, I've got velocities. So this drawing fits that. This one doesn't. Now, here's what I'm going to do. I'm going to go in, and I can leave some of this information on here, but this is all copied on the one to the right. And so what I'm going to do, get rid of a bunch of this. We keep my areas there because those play a role. And this is copied on the one on the right. So now I've got something that looks like this. But guess what? Now I'm going to add some interesting terms here. Let's say P2, oh, I'm sorry, this is 3, location 3. P3, A3, P4, A4, P, this is 2, A2, and this one is P1, A1. Okay. Now, if you look at this, 2 or 3 questions should arise. First question should be, and I'll use this. The first question that should arise is my angles. And just because I didn't do a very good job here, I'm going to say it's 45 degrees here. I'm going to say it's 45 degrees here. So there I sit, and I'm going to say this one's directly backwards. So if you look at the left-hand side of this key equation, you just have the free body diagram kind of equation. You're just looking at the forces. So if you look at the forces, let's do the forces off of this diagram alone, only this diagram, because all my forces are there. So what I'm going to do is I'm going to sum the forces in X first. I'm going to do that equation first, and then I'm going to do the Y below it. So what I got is P1A1. Now you have to realize this is going to be positive. P1A1. Now, do this one. Minus P3A3. Why is it minus? Because it's going that way. And then minus P4A4 over square root of 2. Now, before I go any further, I picked 45 here for a reason, to simplify things, and that is the sine of 45 is equal to the cosine of 45 is equal to 1 over square root of 2. So this I'm going to use to simplify. Usually this would be a cosine sine in here, but I'm just going to make this simple right now. Now, this one, the x component goes back this way. This one up here, the x component goes to the right. So it has a P2A2 over a square root of 2. Again, square root of 2, both of these is because the 45 is on both of them. And then I have the one important force, and that is the force that holds the object still, and I'm just assuming it to be to the right. Now I'm going to shrink this down a tad, and now I'm going to do below it, I'm going to do some of the forces in the Y. I'm going to make that positive. No force out of this, no force out of that. But I do get a force out of this, and I do get a force out of that one. And of course I have my Y component. So only thing I get is I'll start with the Fy because I pointed it north. This one points down. Its Y component points down. So it is P2A2 over square root of 2. Again, if you had something besides a 45, you'd have to deal with sines and cosines. This one points north. So it's a positive. P4A4 over square root of 2. And that's it, because this, no Y component, and that, no Y component. Now, let's slide over and take a look at the right-hand side. in the right hand side, you've got an interesting issue here. And what I'm going to do here is I'm going to set this problem up, and I'm going to go ahead and shut down the lecture, and I'm going to solve it next time. So let's look at the x. So first I'm going to write this out. Controlled sum of the control surfaces, Vx, rho, V dot n, A. So what I have to do legally is I have to go to I have to start and go around the whole surface. That's what this basically does. It'll go around the entire surface and sum it. However, when I'm talking about the walls, all along these walls, the V dot n is equal to 0. Why is that? Because along a wall, and I'm just repeating myself, so if you're looking along a wall here, then say the fluid's coming through here. The velocity is going this direction. The normal is going perpendicular to it at all times. So here's your normal, here's your velocity. Unless there is some sort of mass or something like a hole drilled in which there's a velocity component coming out of the wall, then along the wall, that term disappears. So I'm only interested in the labeled entrances and exits. The 1, the 2, the 3, and the 4. Those are the only locations I'm interested in. So all I do is go list them. V1x, rho, V1 dot N1, A1, plus, guess what? V2x component, rho, V2 dot N2, A2, then plus V3x, rho, V3 dot N3, A3, and then finally V4 in the x component, rho, V4 dot N4 and A4. Again, let's look at this. Here's what you will have to recognize, and you know this already. Scalar, 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 and a scalar. Every other term here is a scalar as well. You know, the area is just a number. This is a number, has no direction associated with it. So I can go in and list these. And before I do, here's what I'm going to do. This is why it's easy to do lectures in this form. Let's do this. Guess what happens here? I'll do a copy, and I will do a paste. So guess what happens now? The bottom equation is the y equation. So, believe it or not, all I do is start in here, replace that with a y, slide it across. Everywhere I see an x, I replace with a y. Everywhere I see an x, I replace with a y. Everywhere I see an x, I replace with a y. And everywhere I see an x, I replace with a y. Now, it's shifted a little bit because the term is back this direction. So what you see is you see two equations, one in the x and one in the y. Now, what I'm going to do is, since I have them both copied, I am now going to move the y down quite a bit, actually, so that I can work on the x, and hopefully by the time I reach this point on the page, I will only be looking at the y. So the y goes from here down. Let's go back and look at the x. And what I'm going to pay attention to mostly is the right hand side. Again, I'm going to go slow, and then this lecture is going to lap over into next term, next period. But when I look at this, now how do I interpret each of these terms? Well, I'm going to look at the right hand side for a while. So let me put my equal sign down here. Okay, so it's true, rho is equal to 1.94 slugs per cubic foot, but I'm not going to put that in yet, and I'm just going to carry it as a variable for a while. So the key is this term, not hard. This term, not hard. Not easy to misunderstand. It is just that area. Easy enough. This is where you might misinterpret things, right here, right here. So I'm going to focus on these two spots for a moment. And I'm going to focus on each of them. So what you're going to find me doing is carrying things here. So let's look at what is the x component of velocity at location 1. Now what I need to do is I need to realize, and I should have done this earlier, x goes this way, and y, of course, goes this way. So since that goes directly to the right, that's going to be just simply plus 20. Why plus? Why do I need to even put a plus? Because it's directional. Since this is going to the right, and the right is positive, then it's okay. Now I'm going to go ahead and carry this. Now what goes here? Well, let's look at this real close. Okay, I've designated this to be like our control surface here. This is basically the normal points this direction. Since they are in opposite directions, they're actually V1, the magnitude of V1, the magnitude of the normal, cosine in their opposite direction. This term becomes a minus 1. This becomes 20, this becomes 1. So what do you get? You get minus 20. And you can see I'm just carrying the A1 because that's not hard to determine. So now let's look at V2 in the x component. Okay, V2, here's your V2 as a vector. Very terribly drawn, but now let me try to shape it up. I have an x component this direction, and I have a y component that direction. So this is V2x, this is V2y. This is V2, which is the 20. So it turns out, since this is 45 degrees, doesn't look like it, then V2x is going to be, or let me write it this way, let me go up to the top. V2, as far as a vector goes, minus 20 over square root of 2i plus 20 over square root of 2j. That is actually the vector right here drawn in vector component. Now, I'm going to use that. And what I'm going to do, I'm having to shrink down to where I can fit everything there. I think actually, that might feel better. So if I go in and do that, then I can say I'm using I don't know where my pen went. It seems like it disappeared. I don't know. So in any case, what you have here is a minus 20 over square root of 2. Why do you have the minus 20? Because it's the x component, and the x component is in fact that part right there. Now again, just carrying the row. Now V2, N2. This part, I'm going to have to pay close attention to. So I'm going to chew up and remove some of the stuff I put in here from before. So it's true, this is V2. Normal, okay, this is something that I guess I should have talked about. Normal always points out of the control volume. So the normals always point out, like a porcupine. So this vector is going exactly in the same direction as that one, meaning that if I'm looking for, and I'm going to write it here, but I'm going to go ahead and V2 is equal to the magnitude of V2, magnitude of N2, and the cosine of the angle between them is 0. This becomes a 1. This becomes a 1. This becomes, in this case, it becomes a 20. So from that, you can put the number in as a 20. And I'm just going to put A2. Now, let's go back and compare this one, the V2 dots. Now, why is these signs different? Well, because this is a flow in, the more velocity, and this is a flow out. So it was coming out up here. So if the flow is going out, it's going to be positive. Some people will be able to adapt to that fairly quickly. Some people have to think about it. I have to be the instructor, so I have to explain every step. So now let's look at the x component of the third. This is the third velocity. It is going directly to the right, and it's 100 feet per second. So it's just simply plus 100. Now remember, this one was minus. Why was it minus? Because it was going backwards. Carry the row. Now, V3.N3. Okay, so if you zoom in on it, yes, normal goes like this, velocity goes like that, so it just becomes 100. So you can start with this concept of, okay, this is 100, so what I'll do is I'll say out, out, in. Okay. A3, I'm just carrying it because that's the easiest thing to understand. Velocity of 4, the x component of the velocity at 4. Okay, here, I've got a velocity that comes out. I've got an x component, and I've got a y component. So actually, if I want to write this as a vector, it would be this number over square root of 2. Why? Because it's 45. And it's going to the right, but going down. So this vector going down in the negative, in the opposite direction. Looks like that. So all I'm doing is plucking the component right there. And got my density. Now, it turns out it's going out as well. So since it's going out, I can just copy that down in A4. Let me discuss the out and again. There you go. Here's your normal. If I want to be kind of silly, I can say 1 over square root of 2i plus minus 1 over square root of 2j. That's the actual normal vector. And if you dot it with that equation, the square root of 2 comes up and hits this square root of 2, gives you a half. This square root of 2 comes up, hits this square root of 2, gives you a half. Then you got 33 and a half over 2, 33 and a half over 2, minus and minus become a plus. And you find out you get back 33 and a third. That should be a third right there. So, in fact, that's your lower part of the equation. So now you can go ahead and put in your 1.94 so you know. Okay, so here's what I'll do. A1 is 2. So I'll say this is 2. This is 1.94. Area at 2 is 0.5. 1.94. 1.94. Area at 3 was 0.2. The area at 4 was 0.3, and this 1.94. So believe it or not, you know every number in this part right here. We'll come back tomorrow and figure that part out. And I'm going to go ahead and close it down right now. And say we're going to be done. We're going to pick up exactly where we are here. And so I'm going to go ahead and drop us off.